computer. Okay, so hello everyone. Thanks again for being here today with us. As always, thanks a lot for joining this initiative, and I think everyone is learning, including me. So let's continue doing that. Today it's day 3 of the RH class. We will continue with the configuration of the atoms and things related with the non-NLTE computation. In particular, we will learn how to set appropriate values for the non-NLTE iteration or non-NLTE problem. This is something that we will check in detail later, and I hope you will get an idea of the meaning of the values and how to set default values that will work most of the time. We will also compare the results of the calcium 8542 computation for those specific tests where we play with the non-NLTE iterations to check that they have an impact on the final profile. And I hope I will help you to really define a value that will work most of the time. And also we will learn about an option that is called NG acceleration that is also included in the configuration file. And it's sometimes that something that sometimes we use as default, but we may not really understand what does it mean or what is the impact on the computation. So I will try to spend some time on that today. So then I hope it will be helpful for you for future computations using either RH, stick, or design, because this is something that is used in all the codes. So then let's jump to the script. As always, we are going to check files that are in this folder that I created, and then I will share with you. It's called atomconfig2, and I have it inside my RH distribution and then inside RHF1D. Okay, so we are going to mainly use 2 files today, this script and then the keyword.input. But just as an example, I have here the atoms.input, just to show you that this is the same that we had from last week, where calcium is set as an active atom and the rest of atoms are passive. And also we are going to use the same configuration that we had last week, that we said that was a reasonable one, where we put 70 wavelength points and we distributed them in a linear way with these 5, the Q core 5. Remember that this can be translated to wavelength with the equation from last week. And then we reach in QWin until 150. Okay, so this is the same as last week. So now let's try to understand a bit more about the non-NLTE problem itself. So then if we go to the keyword.input, as I said, there are a lot of items that we can fill. So I'm going to try to go through them just related with specific cases. So in our case now we go until this point, that is the maximum number of iterations that we want to use and the iteration limit that we want to define. So then, as I said here, let's start with something that we can call LTE. So then we just put 0 here. Just let me put ID alone. And then what I'm going to do is as previous week. So I just compile, I run the code and then I solve array and then I read everything. And then I read also, I compute the projection with a heliocentric angle for mu = 1, so this center. And I read that file and I just save it for later on doing a comparison. So then when I'm running this, I will show you the results. So just let me compile the script. So then the code worked. There's a lot of message, but it says basically that it was reading the atoms and the atmosphere, and then just this. Okay, so no additional information, no iteration. Okay, So then if we read these, the wavelength for this example and intensity for this example, I plot it here. So then we can check the results. In the day 3, you will have these plots. So let's start with the first example, so no iteration. And the profile looks like this, okay? So then we have that the line looks smooth, but it looks a bit wide. And also the intensity in the core, it's a bit not realistic. So then
Carlos,
yes.
Sorry to interrupt.
Yes.
Did you put in the atoms.input input the initial population or the starting solution as NLTE populations?
No, so then this is the reason why it was wrong. I was looking at it and I said, okay.
Yes. Sorry, I should have.
Yeah, it was
before.
so.
But this is useful to know.
Yes. Yes. So then let's repeat it and then we will check that. Okay. So we stop here then. Okay. So then and now I'm going to check here. So now it should be. Well, I didn't save the file. Sorry. So just let me do this. Now I will save the files. Yeah, and I think now we are, yes. Okay, so then let me comment these, and now let's check if I did it properly. Okay. Yeah, I saw it and I said it looks wrong. I will ask Han, but for this example it's basically okay, because then in the future I will show everyone how to do the LTE computation with the Kurux line. So, but yeah, now it looks a bit different, but still it looks a bit weird. So then at this point, let's say what I wrote. So yeah, so I wrote that the profile looked more or less okay. In the previous one, it said almost 0, but now I have to change this. But basically, the idea is that if you want to compute lines with RH in LTE, probably the best thing to do is to do it through the Kurux line list, and we will cover this in the future. So for now, assume that the orange profile that I have shown you, it's not the best thing that we can do if we are focused on LTE. Okay, but the important thing is that if we don't iterate, it means LTE for RH. So now let's try to do a different thing. So just let's put one iteration. Okay, so in this case, as I said, I'm putting this in the keyword, and now I'm running again. Just let me remove this stop and then this stop. Okay, and I have a stop here. Okay, so then if we run with one iteration, you can see that again the code is writing a lot of things, but now it's writing iteration 1 and it's giving you some information. Okay, so then what I had from the previous case was this one. Maybe it's because I put LTE populations. Okay, so what I wanted to show you is that if we do just one iteration, this value, it's not close to the iteration limit. So then if we plot the profile, that I think should be this one, let's see if it's updated. Okay, so now we have the blue one that looks more like a traditional calcium profile. But if you are used to analyze calcium data, you will see that this profile, it looks like the line core is a bit deep. Yes, yes. So then the idea is, yeah, you're muted, Han. You can. Okay. But yeah. Okay. So then Okay, I cannot hear you, but I think I understand what you're saying.
Sorry, don't worry. I was replying to another message, but
Okay,
I
okay.
accidentally replied to everyone.
Okay, okay.
Yeah.
Okay.
So
okay.
yes.
Okay. So then yes, it doesn't make sense, this profile. So the idea is, if you start doing iterations like I have done with 1, then the blue line looks like a absorption, a calcium 8542 profile. But the line core is probably deeper than we expect. And also in the previous example, just let me check, because I had, just 1 second. I think I had this. Okay. So then, because this is what I copied here. So then this value, it's very far from traditional iteration limits that we put and when solving the non-LTE problem. So what I'm trying to say here is that you have to put iterations, but if you put only a few, the code will just run for the number of iterations that you are providing here, but it may be a solution that is not close to the one that you want to achieve. So in other words, it's not solving the non-LTE problem with a high accuracy between the statistical equilibrium equations and the radiative transfer equation. So it's important to provide more iterations. And then the advice that I want to give you here is that my recommendation is, if you define a relatively normal iteration limit like this one, and you put a big number here, like imagine 1000, the code will reach this iteration limit much earlier than 1000, probably in 20 or 50 iterations. So my recommendation is to be generous in the case of maximum iterations, and relatively demanding in this case. We will see what means 1 to the minus 3 or 1 to the minus 2. But if you only put like 10 iterations, you may not reach a fully compatible solution between the statistical equilibriums and the radiative transfer equation. So please always try to keep a large number in this case. So then when solving the problem, you will have a high accuracy for the non-LTE problem. Okay, so then what I proposed was 50. So let's put here 50. And now we are going to remove this stop. And I have a stop here. Okay, so then I compile again. And then you saw that now we had much more iterations. And we can go back to see them. So you can see that the code is saying 13, and you see a value here, 14, 15, 16. And then at this point, it has already surpassed the limit. So this value is below 1 to the minus 3 already. So then, as I said before, if you put a relatively large number here, most of the times the code will reach the iteration limit earlier than that point. So you are not really making the code go slower. You are just guaranteeing that you are obtaining a good accuracy when solving the non-LTE problem. Okay, so then let's compare now the new profiles. So now we are here, comparison. This is including the new one that now it's this orange one. And you can see that the new one, the red, it's so orange is LTE. Blue, it's one iteration. And then red, it's reaching the iteration limit. It took 16, but it's reaching the limit that we have established. So you can see that the wings are in general similar between the blue and the red, but now the core, it's different. It's a bit smaller, and I think it's more realistic. And this is essentially because, as I said before, with a few iterations, you are not really obtaining a fully compatible solution for the non-LTE problem. Okay, so then please keep that in mind. And now I've said that the red profile looks more like the observations, but the truth is that we should check that, and there's a very easy way to do it. So let's look for the atlas.
Carlos, yes. Can I just, for clarification,
yes.
that since I have had a few messages, people asking why LTE would show.
Okay.
So what happens physically is that when you put in the atoms not input the starting solution as LTE populations,
yes,
the code when it iterates the non-LTE population has to start to figure out some starting solutions, and one of them is the LTE populations. And if you set that, the code will use the Saha-Boltzmann equations to calculate the population numbers and do the formal solution with those population numbers. Yes. So when you have a chromospheric temperature rise, I'm not sure which model you're using. Is this the FALC or what?
Yes, we can see it. So just let me analyze. Atmosphere model. Yeah, it's the FALC.
Yeah, okay. So when you have a chromospheric temperature rise, then the populations will determined by the Saha-Boltzmann, and you calculate the intensity. The intensity will just follow the temperature. So in the line core, you will see the chromospheric temperature reflected in the emission peak, in the central emission peak. And so that's why you get the shape that you get from the LTE calculation. Just wanted to clarify the physics behind what's happening.
Yes, yes, but essentially we should not use that at all.
Well, it depends on what you want to do. But if you want to compare with actual solar profiles, then it doesn't make sense. Yes.
Yes. Yes. Okay. I think Dato has a question.
Yes. So Carlos, if you have the high number of iterations, does it still important that the initial what you will indicate in the initial solution?
Well, so typically sometimes either of the two is closer to the final solution, so the convergence is a little bit faster. And B, sometimes one of the two may be so far off that actually the code gets lost, so that it doesn't converge. When you have, in a simple case like calcium, where you just have the 5 levels plus continuum, that typically doesn't happen. But when you have a lot of transitions at many different wavelengths, some of them very high in the infrared or so, you might sometimes get lost. Helium is one such case where you have to be careful. And there's no specific rules for that. Sometimes when it doesn't converge, you try one thing or the other. We will talk about NG acceleration later. That's the tricky part in that sense, and Carlos will explain, I'm sure, better later. But in the case of an atom with strong resonance transitions like calcium-2, it is a better initial solution to use the zero radiation as a starting solution, because it's closer to what you finally expect it to be.
I see. Yeah. Thank you.
Yeah. So basically that. So there's no recipe, so we may need to try, but in general, for calcium or magnesium too, you can use zero radiation and usually works well. But as Hans said, so when you have complex atoms, you may encounter convergence problems, and then there are some things that you can tune a bit, but it's never clear which one is the one that is really helping or not reaching convergence. So it's like some trial and error. But in the case of calcium, I would say that we are safe because it's really a robust atom. So in general, we have very good convergence. Okay. So then I was saying that, in order to really compare the new computation and really see that it's closer to the observed profile, so just let's go to the BAS 2000 solar database. Remember, this is, you have the solar atlas here. So in my case, I just type here 8542, and then I put 40 Armstrong just to have a reference. And then if you want to have it for making plots, so you just click in this icon here, and then a window will pop up, and then you have here wavelength and intensity. Okay, so then I have download this information and I put it in a TXT file. So then I just read it here with the ideal routine read call, and then this is wavelength and this is intensity. Okay, so then in order to compare them, we need to normalize them. In the case of the atlas, this database provided it normalized to 10,000 arbitrary units, or yeah, I think arbitrary units, and to the nearby continuum. So each portion of the atlas that you pick, it's normalized to 10,000. And in the case of RH, it's in SI units. So if you remember all the plots that I was showing, it was something up to the -9 or -10. So then what I'm going to do is to pick a wavelength. The plots I've been showing, like this one, you see that the first wavelength is 853.6 nanometers. So I'm going to pick that value for as a normalization. So I'm assuming this is continuum. And the idea is that if you want to look for this value, you basically have to do it by hand. So here I just print. So for example, if you print lam1, that is the wavelength vector from RH, you put 0, this is nanometers. And then if you go to like 140, so then you start to see that we are close to calcium. So then if you print 172, like I have there, you will see that it's close to the one that we assume as a continuum. And then I basically normalize all the profiles that we computed to that value. Okay. And then I looked in the atlas for a wavelength that is also similar to that one. So just let me print this one. Okay, just let me compile everything. So let me remove this stop. Okay. Okay, so then you can see that they are relatively close. So then this is enough. I think it was closer, so I'm not sure if I have changed something, but let's chat. There's a question from Ryan. He says that in Python you can use something like numpy where or numpy. You mean for finding the wavelength? Okay. 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 Good. So, but my thank you. So, but my comment was in the direction that even if we have found this wavelength now, please be aware that if you change the atomic configuration, so I mean, if you change the wavelength points, this will change. If you change also QWin or QCore, it will also change because they will be distributed differently. And also, if you add additional atoms, then the wavelength vector will also increase based on the configuration of N lambda, QWin, and QCore for that new active atom. So just be aware that wavelength vector will always depend on the configuration related to your atom configuration. And if you change it, then you have to be aware that they will change, just in case you are picking a specific wavelength range for some purposes. Changing things in your atom will also change that. So just be aware of that. So then I think now I have plotted these. So just let me check. If I go to comparison, no, sorry, this one, no, atlas. No, this one has not been updated. So just let me see where I was. Yes, so then yes, I run this like this. And then this one is updated with the new, yes, okay. Okay, so then what we have here is green was LTE, and as we said, in principle, in the line core wavelength, it makes no sense. Then we had blue, that it was one iteration, so it's non-LTE, and you can see that the wings between the red and the blue are essentially the same, but the line core is different. And then red was the problem that it ran all the iterations until it reached the iteration limit. And if you compare the red and the black, they are really, really similar. Okay, so wings, as you see, the normalization looks okay because the wings are reaching more or less the same continuum, and also the 9 core is very close. Okay, so this is why I was saying that the one that completed the full non-NLTE solution, it was more realistic. So you can see that black and red, they are very close. Okay, so I added one comment that I would like to remark here is that they are really good. So in general, when you use a FALC model, you are using an atmosphere that was created to reproduce the atlas, but it was based on a specific code that is not arranged. It also used different atoms. It also used abundance that are not probably the same that we are using now. So in general, if you use a good atom and RH, it may not be as good as this one because the FALC model behaves well, but it depends on a lot of factors. So then what I want to say is that this case is really good. In general, it's, okay, there's a chat. Okay, I think there are some messages that to me.
No, it was the answer to Ryan.
Yeah, but I think Ryan is.
What I think he was asking.
No, but he's asking me if I don't see that the LTE line is orange. Did I say something different?
I don't know, Carlos. I was trying to answer.
I think you said green, but that's okay. Doesn't matter.
Okay. Okay. He's saying me that it's orange and not green. And sorry if I said green. So the idea is, what I was saying is that this case is a very good case because the atom combined with RH and with abundance and with different things, plus the FALC model, we are getting very close to the atlas. So then this is very promising because it means that the atom it's really good. And I think this is also very good in terms of future inversions, either with a stick or with beside that are based in RH. So this is really good. But in general, be aware that some atoms and plus FALC, they do not match as well the atlas, but this doesn't necessarily mean that it's wrong. Okay. There's a different question to me. I think, please, you can ask, because if I try to read the chat while I'm speaking, it's very bad. And also people can understand the question. So Harsh, is it possible that you ask the question?
Hi, Carlos.
Yes.
My question is, so question is, I was just wondering that whether LTE level populations of concerned transition would be higher or lower compared to the converged NLTE solution, or it has no relation whatsoever.
So I'm not sure if I fully understand. So you mean the final populations from solving the non-LTE problem, if they are going to be higher or lower than the LTE ones? Is this your question?
Right. On the concerned optical depth, suppose if we talk about the line goal, then we might see level population of log tau -5 with and without LTE. What will we see?
I'm not sure. Han, do you want to
Well,
comment?
some of the population will be higher, some of them will be lower. You can plot the population numbers, but maybe not so relevant now. But they are available, and you can plot the departure coefficient, which is the ratio of the population numbers. But in general, when you have deviations from LTE, they may be positive or negative.
Yes.
They're not necessarily always positive or always negative.
Yes. Yes.
And
Yes.
to
So
depend on what the radiation field is doing to the population numbers.
yes. Yes. I think as a context, what we use for design is the departure coefficients. So are the deviations from LTE of those non-LTE populations, and then we use this as a correction factor. But as Hans said, sometimes could be positive or negative one, higher or lower than one. And then we just add it, but we don't really check if they are always positive or negative. We just add the correction respect to LTE, and then we are doing something like non-LTE. Does it answer your question?
Yes,
Okay.
thanks a lot.
Okay,
Thank
okay.
you.
Okay, thanks for doing question, but please, as I said, if you answer them directly, then people can understand, can listen to them and can answer them, and then I can also be able to listen and to answer, because reading the chat and trying to speak, it's a bit difficult. Okay, so then until this point, the main thing that I wanted to show you is that you need to add. Let's go here to the iterations and the iteration limit. So you need to add a given number of maximum iterations. And my advice is just do not restrict to a lower value, because adding larger values doesn't mean that the code will be slower, because it probably reaches the iteration limit before reaching the maximum value. But it's important that the value should be high enough. Otherwise, you will not reach the iteration limit, and then the solution will not be good enough. Okay. So is there any question until this point before I move to NG acceleration? Okay. So then here in this case, this is from the previous computation. And if you remember, we were running iteration 14, 15, and 16. And then this case was already below 1 to the minus 3. But if you check here, there's a label that it says accelerated. So then in this case, it means that in iteration 15 is being using the NG acceleration method. I think there are several papers. I was not really looking into detail, but I think this one is very good, because they compare different schemes and how it improves the convergence speed. I downloaded the paper and I put it in Dropbox, so you can download it. But probably there are additional papers where you can read what is really NG acceleration. But the important thing is that it's a process where you try to accelerate the convergence scheme of the non-LTE problem. Okay, so if you go again to the keyword input file, so you can see that the next sentence after iteration, it's NG acceleration, and you have different values. Delay, it means that the acceleration scheme will start at around iteration 10. And then this order and period are a configuration of the scheme. And in general, I think you can leave it like this, but I believe in the manual, there's additional information of the meaning of these two. But this one is probably the one that you may play with at the beginning, and is when you want to switch on the option of running NG acceleration, or if you comment the line, it will not have NG acceleration at all. So then if we checked the example that we have run, starting from iteration 8, you will see that it has -2 here, then it says -1 accelerated, and then it jumps to -3. Then it says nothing, and then it says accelerated again. Here it seems that it's worse, and then it goes down. And then here it says accelerated, and then it makes a jump. So when I was checking this, the truth is that, for example, in this case, we were at -2, then it's -1, but then it suddenly jumps to -3. I had the impression that it's improving, but acceleration itself, I was not sure. So then I said, probably you will not be able also to really see that it's improving. So then the best thing that we can do is just repeat the test, but commenting the line. Okay, so then we run again the computation, And then you can see that in this case, I have printed in the script, but we can go through the terminal. So if we start from iteration 14, we can see that we have 15, 16, and in fact, we have to run until iteration 22. So in the previous case, although we saw those jumps, the code reached a value lower than 1 to the minus 3, 1 times 10 to the minus 3 in iteration 16, but without NG acceleration, it's going slower. You can see it's 7 to the minus 3, 5, 10 to the minus 3, 4, 10 to the minus 3, 2.8, 2, 1, sorry, I was reading the wrong values. So 2.5, 2.1, 1.5, 1, and then it goes to the minus 4. So then, even if it's not clear how was doing the jumps before, now you can see that it requires more iterations if you're going to add the NG acceleration. So adding it, it helps. And in fact, I added one pixel, one example with a bifrost pixel. We will have atmosphere. We will use it later on in the course and tutorials. And it's the enhanced network run created with the bifrost atmosphere. So then if we go to this place where we are providing the information about the atmosphere and we set bifrost, I have already put this atmosphere in the folder. So then we run it. So then we see that we need 35 iterations to reach 1 to the minus, so below 1 time to the minus 3, 10 time to the minus 3. And the idea is that this is because the atmosphere is a bit more complex, but just as a reference, if now we add the NG acceleration and just repeat the same computation, then it's faster. You already have seen it, but you can check the iteration where this was achieved and it's in number 20. So then we needed 15 more non-LTE iterations if we don't use the NG acceleration. Okay, so then just have it as option to accelerate the process, and in general it works. And you can leave it like this if you have a big enough number here. But in fact, depending on the convergence rate of your atom, you can play with these numbers. Okay, so after saying that, I would like to add a warning that is for complex atoms. Sometimes it's difficult to really get a good convergence. So in those cases, the NG acceleration could be a worse thing because it can really make a big jump in other direction. So instead of helping going down in the iteration limit, it goes away and then the code crashes. So then in those cases, you should really start first without NG acceleration and check that you have convergence. And then if that is the case in general, then you can play with NG acceleration. But maybe if the code is so, if the atom is so big, for example, imagine that you have, I don't know, a 16 level atom or 100 level atom that is much larger than the calcium one we use. So maybe you need 100 iterations to converge. So then probably in that case, you may play with, instead of putting 10 here, you can put 50. So then the first 50 iterations, the code, it's slowly getting there. And then you start making jumps in the convergence rate after 50. And then probably you are closer to the solution and the code will not crash. But this is something that you need to experiment a bit. So the important thing is, for this case, in general, it works better with NG acceleration. It's faster and it converges well. But it will depend always on the atmosphere and the atom that we are using. Okay, so then as a summary, Han, do you have comments?
Wanted to
Yes.
say a few words about what the NG acceleration does and why sometimes it fails or sometimes it makes things worse. So if you read the original paper by Rybicki and Hammer, that the RH method is based on and named after,
Yes.
Then they say that, or they show mathematically that with the iteration scheme, you are guaranteed that the population numbers stay positive, which is really important because in radiative transfer calculations, you have terms like e to the minus tau. And tau is the optical depth, and the optical depth depends on population numbers. And if you have negative population numbers, you get negative tau. And so terms like e to the minus negative can become a large positive number, and then things can explode.
Yeah.
Now what the NG acceleration does, it is a mathematical formalism that tries to extrapolate a series of iterations and tries to guess mathematically the best next iteration. So it extrapolates a number of, and this is what the order and the period say. So the order is the number of iterations that it uses to predict the next, and the period is how often you do a regular iteration before you do attempt another acceleration. And the delay is, as you explained, is before you is the number of iterations you do before you start doing this kind of iteration. But what may happen is that if you have complicated situations, the NG acceleration doesn't know anything about the physics, so it makes a best guess. But you may end up with negative population numbers in some cases, which makes the scheme explode. Yeah. So that's not good. So typically in complex situations, it's better to increase the NG, the delay. Sometimes it's beneficial to actually increase the period so that you do more actual iterations that take into account the physics, then every now and then only do attempt an acceleration. Sometimes you can increase the order. You can increase to 3 or 4. I don't think it's useful to do more than that. But it's something to be aware of, that this is a mathematical process, not a physical process. And that's why you sometimes can get into trouble when it over-eagerly tries to change population numbers that it shouldn't.
Yes. Yes.
But
Okay.
you basically are... Yes.
Sorry. Can I ask a dumb question?
Sure.
So if the NG acceleration producing negative populations makes the scheme explode, why can't you just add a little check so that if the acceleration attempt produces negative populations, then discard that and do a regular iteration?
Yes, you could do that. That's might be a good idea.
I think that the idea is that this is one of the cases where you can have problems, but it's not the only one. So even if you have proper populations, maybe the scheme does not work properly, and it's not exactly that the populations are negative. So essentially the idea is that if you put NG on and you are doing a complex computation, 1D or even 2D or 3D, the code may try to do something that is not at the end the best thing, and is not able to recover from that. And how you define the recovery process is not so straightforward. So I think this is the key. So if it's only that, then it can be implemented. But sometimes there are some things that are not so easy to set. I put a flag and then from there we recover. So essentially, I think it's the best thing is to switch it on. And if you see convergence problems, if you switch it off and it works, then we need to evaluate what is happening.
Yeah. Well, and there's also the cost and benefit comparison, right? The NG acceleration takes some extra effort. Yes, you cut down in the end the number of iterations, so that's good. But if you make the NG acceleration process more complicated, you lose some of the benefits. If after every NG acceleration you have to compare population numbers and say if they are what you expect them to be, then you add a cost. So yeah, it might quite well be that cost is very little and that it would actually help.
Yes.
But also, you at some point you don't want to make your code too complicated.
Yes.
Okay.
Yes.
And I did have one other question. Sorry.
Sure.
So in this context, complicated problem, I know you said that usually means like a very large atom with a lot of levels or PRD. What about multiple atoms? Like if you had multiple simple atoms, is that a similar level of complexity to a single massive atom?
I think with regard to the NG acceleration, not so much. What the problem is with multiple atoms is that the linearization and preconditioning scheme that has for overlapping wavelength is not optimized for multiple atoms in the sense that it doesn't take into account cross-term corrections where there are transitions of atoms that overlap in wavelength from different atoms. So that's why in general that will converge a little bit slower.
Yeah. And also it will depend on the atom. So I mean, in fact, I wanted to ask you as a homework to do this, but we can do a test now. So if we put active this atom, so now we will have two atoms. One is sodium, and I think this is 11 levels. So it's a bit more complex than calcium, but not crazy complex. So if we run the code now, you can see that now it's getting slower. But basically the one that is defining when you reach the, so let's go back. So in this case, you can see that calcium in the last line, last iteration was already up to the -5, but sodium was the one that was not reaching below 110 to the -3. So in this case, I think it's more or less the same if the atoms are relatively in the same level of complexity, you will reach the convergence. The only thing is that you may need more iterations because some of the atoms will go slower and the code will try to reach the convergence limit with all the atoms. So one can be very good, but until the second one is not in the iter limit, it will try to continue doing iterations. Okay. But in this case, it's accelerating and it seems that it's doing it well because before we needed like 20 iterations for only calcium. And in this case, with 25, we solved the two atoms at the same time. So yeah. And in this case, I think the reason why you saw that it's becoming much slower is that because you have more levels, then you have more transitions and you have more wavelengths. And then the problem is becoming more complex. But I think I would say that if you have reasonably similar atoms, you can keep the same configuration. And unless you see that in some cases you have big jumps in one atom when using accelerated, then you can start removing it or playing with the delay. But in general, I would say that for normal atoms, that between 5 or 10 levels, you can keep it like it is in this example.
Okay, and of course, this is all for a fairly well-behaved atmosphere like the foul sea. It would be different, right?
No. Right now I'm using a PFROS simulation. So this is an example from a 3D MHD simulation, and it's working well. So if I put foul sea here, it should be a bit faster.
82.
Yes. So the previous one was was 25 iterations, and this one with the foul sea, it's 16, but it's not a big difference. So yeah.
Okay.
Yep.
I don't know if you have time still, Carlos. If you want to demonstrate. If you want to demonstrate a case where you really have to wait with NG accelerations, you can do a helium 1.
Okay. Is it this one?
Yes. Okay. But you have to put the proper atom.
Okay.
Actually, I'm not sure if you have it. So
I'm not sure.
I hope you do. I
No,
hope you
I'm
do.
not sure. Let me see. Let me see. So I go to the distribution
To the
atoms,
atoms.
and then let's see helium.
I'll go to here. Oh, yeah, I think you might have it.
Yes, helium.
So yeah,
one of these.
this one above that.
Okay, this one.
Yes.
Okay. Okay, so then let me go back. I think this one. Let's see if this works. Okay.
Yeah, and so
Yes,
set the
yes.
other ones to passive, just to
Oh,
not.
can I
not
try
yeah.
like this? Yes. Is it okay like this?
I
Or-
mean, yeah, you can, so,
Yeah.
but then we don't know what is the complication. So
Yeah, if we see that one helium is not converging and the others are converging, then
yeah,
so you can see that this one is in fact increasing, and then now it's moving out. Yeah. So it's
so yes,
yeah, I saw up to 10 to the 2. So the one.
yeah.
So you can see that
So-
the others are up to -8,
Yeah,
but helium
yes.
is not working.
Yes.
Yeah, sorry, I can. So then you said that if I switch off NG
So
acceleration,
then say delay NG acceleration till
Okay.
15 or so, or 20. I think 15 is usually what works in
Okay.
a pulse C.
okay, so then let's put here 15.
Yes.
Okay, let's see. Yeah, that's going
Eh,
down.
Yeah.
Yeah,
So now it's
and now it's going back.
no, it's still no.
It's
See,
going back.
so see, I mean, that's
Yes.
the complication also with the other
Yes. Yes, let me try
atoms.
just without acceleration,
Yes.
and then let's see if, because it was going down slowly but
Yeah.
going down. So
Yes.
okay, so this one, yeah, it's going down.
Yeah.
Yeah. Yeah.
So with other atoms present, you might even have
Yes. Yes.
to do this.
Yes. So yes. So then I think this is the example I was thinking about, because yeah, as NG acceleration was making things going
Worse.
in the wrong
Yeah.
direction.
Yes.
So yeah. So it didn't reach the 1 to the -3, but I guess if we just add more iteration, it will work, because it was going.
Yeah, it will eventually converge. Yeah.
So yeah.
Yeah.
Okay.
So that's
Okay,
a clear
thank you.
example of
Yeah.
where you have to be careful. Yeah.
Yes. Okay, so then
I have a question.
yes.
Yeah. So I had observed that compared to static case, if you implement the velocity in the problem, then the code converges faster than that of the static case. So any comment on that?
So please, can you repeat? You added a velocity and then
in
the
the
convergence.
presence of velocity fields, the code converges faster than the static case.
Oh, that's interesting. Well, there may be two reasons for that. I mean, I don't think in general that would be the case. One case is that when we have a static atmosphere, the formal solver, so the part of the program that calculates from the source function, calculates the intensities, is different. So in the static case, it uses the Fourier solver, which is a second order differential method. And when you add velocities, it will switch to a short characteristics. And I think by default, it's now the Bézier one. So the intensities are slightly different. And so that there might be some differences in the convergence there, because of those reasons. And maybe physically, when you add velocities in a certain way, the problem becomes a little bit easier for the radiation field. So it might as well converge easier that way too. But I think the main difference is probably the difference in formal solver that you use when you have velocities or not velocities.
Physically, can it be commented that velocity, I mean, the photons escapes easily, which may also Can we combine?
Well, yes, I mean, that could be, but that would require really large velocities.
Okay. Okay. Thank you.
That would really require velocities that you don't really see in the photosphere or the chromosphere.
Okay. Thank you.
I had a quick question about the example we just did with the 10830.
Yes.
So Han, you said that for chromospheric lines like the calcium 2, you should start with 0 radiation because that's closer to what you experienced.
Yes.
For the example that was just done, the helium atom was left at LTE populations. Could
And
that
for
be
helium,
part of why?
Well, helium, I don't know exactly. The helium, it works better with the LTE populations as the starting solution. So even though we didn't change it, that happens to be happily the best solution. But
Why?
Helium doesn't have in the helium 1 doesn't have any strong resonance transitions in the visible, where most of the photons are. That its lines are so far to the ultraviolet, where the radiation field is small, that I think that LTE is still the better starting solution. So it works well for calcium and magnesium to start, and hydrogen to start from 0 radiation, because they have very strong lines from the ground level, and 0 radiation field basically mimics the photon escape in these lines, and that gives you a better solution. But that's not the case for helium. I think there's an interaction between the lines and the ionization, and so it's more complicated than that.
Okay. So any additional questions? Okay. So then in summary, what I wanted to really focus on today is that you need to iterate for solving the complete non-NLTE problem. And I recommend you to set a large number of iterations, because in that sense, you will always reach the iteration limit. Otherwise, you can have a wrong solution, even if the code has converged. And in the case of iteration limit, usually 1 to 10 to the minus 3, it's reasonable, but you may play with different values. But it's important to have a large number and to check at least with 1 or 2 examples for your specific atmosphere or your specific atom, if you reach the iteration limit with the number of iterations that you provided. And then the second one is to try to experiment with the NG acceleration. So as you saw, it's clearly faster with calcium. It was also faster when we combined calcium and sodium. But in the case where we added helium, it was making it worse. So then it's something that you have to play a bit. And in general, when you have really, really, really large atoms, then you can see a big difference. But for example, for the calcium, I would say that we were saving like 0.5 seconds. So if you are going to do massive parallel cluster, then saving 20% is probably not a big issue. But with complex atoms that can take 10 minutes for converging, then saving 5 minutes or something like that, or 2 minutes, it's a big jump if you are planning to do a big computation. So then I would use it as default, but just check for at least few pixels that it's working as intended. Okay, so then let's go back to the presentation here. Okay, so then the homework is I recommend you to just make a test. So if you remember, I run it to up to 10 to the minus 3 and I compare to the atlas. Maybe you can try to run it with more iterations up to 10 to the minus 4 and just compare with the atlas again and compare between the both solutions and check if the extra time that you added, it's enough to see a change like we saw from one iteration to the final 10 to the minus 3. This is what I have said. And then this is exactly what I had in mind for as a homework. So just set sodium as an active and run it and just check how it works. And you will see that different atoms, they have a different convergence rate. And as I said before, in general, if you have enough iteration numbers, the code will push all the atoms that you have as active to reach the iteration limit. Even if one or two of them have already reached it, it will try to push the others until you have the best solution for all the atoms. Then next class, we will continue with RH. I think we will jump to PRD, to partial distribution. I may use calcium H and K, or I will just use a simple atom of magnesium 2, H and K as well. And we will see the differences, and we will learn one way of visualizing those differences that then you can use later on for a different transition of interest, where you are not so sure if that transition is sensitive to PRD or not. You can do the test that I will show you next week, and you can have an idea of the impact of PRD on the transition. And it will be next Friday. Okay, so yeah, so before I stop sharing, is there any question related with the code itself or with something that we saw today? Okay, so then I stop sharing. So no questions, last chance. Okay, so thanks a lot. As always, it's a pleasure to having you here and also asking questions. Today was fun. So please come again next week and let's continue learning. Okay.
Thank you. Bye-bye.
Thank you so much.
Bye, everyone.
Bye.
Thanks and bye.
Bye.
Ciao.
Ciao.
Bye.
Ciao.